Bismillah ar-Rahman ar-Rahim. Assalamu alaikum, dear students. I am Arif and I welcome you all to the next session of the video series on the subject of system programming with Linux. The title of today's session is C compilation process from a system programmer's perspective. Well, in today's session, we are going to review the C compilation process in detail. We will see the contents of all the intermediate files using the readelf and objdump commands. We will see the different formats in which operating system store the relocatable object files, the executable files, the shared object, and the code dump files. We will also see how an executable file is loaded into memory to make it a process, and how a process is logically laid out in the memory. Finally, we will see how a system call can be invoked using a C library wrapper function, without a wrapper function, or from within the assembly code as well. Let us start playing. Well, dear students, this slide gives an overview of the C compilation process. The first thing you do is you write your C code in some text editor, the source code writing. I will be mostly using Vim. You can use Pico, Nano, or gedit for the purpose. Instead of using a simple text editor, you can also use some code editor like Genie or Atom, which provides features like code completion, hints, highlighting sections of code, and maybe the custom folding of the code sections as well. Since code editors are limited to writing code only and do not go beyond this stage, so some of the developers might prefer using some integrated development environment like CodeBlocks, NetBeans, or Eclipse CDT. Well, these IDEs, as you all know, are self-contained packages and allows you to write, compile, execute, as well as debug your code in the same place. Well, these IDEs give abstraction to a lot of underlying details. So being a system programmer, I recommend that you should use Vim in the beginning. Well, once we have written the code, we will let it go through the famous 4 phases: the pre-processing, compiling, assembling, and linking. Let us move on a Linux terminal and run these phases one by one. We're going to use the GNU GCC compiler. Well, GNU Compiler Collection basically is an integrated distribution of compilers used for programming languages like C, C++, Objective-C, Java, Fortran, and Ada. Right now the version is 7.2. Let us see information about the platform as well. uname-a. Okay, the hardware is x86 64-bit running Kali Linux, and the kernel version is 4.9. Okay, let's see a basic hello program. Let me move on to this directory and get hello.c. Well, this is a very basic hello world program having single statement that says printf welcome to system programming with Arif Bhatt. Let's do the pre-processing. GCC -e. This -e option basically instruct GCC to do just pre-processing. And let me redirect the output to a file hello.i. Otherwise, it will be sent to the std out. Well, dear students, the pre-processing phase actually interprets the preprocessor directives. It includes the header files, remove the comments, and expand the macros. And from this .c file, it generates another ASCII file having a .i extension. And we can use the less or the cat command to view the file hello.i. Oops. There are a lot of information from different header files that have been included in it. And at the very end, you can see just the 3-4 lines of code we have written. Well, dear students, the C preprocessor searches for the header files in the USR include directory. Let me do ls usr include. This is the location of all the header files, standard location. You can see the stdio.h, stdlib.h, math.h over here. Well, to tell GCC to look for header files at non-standard locations, you can use the -i option, followed by the directory path containing those header files. Well, anyway, let's move on to the next step, and that is compilation. The compiling phase takes the pre-processed file as input, that is this .i file, and generates the assembly code for the underlying hardware architecture. And in our case, it is x86 64-bit. Okay, gcc hyphen capital S hello.i. Let me give an option of using the standard C11. The -s option instructs GCC to do just compilation. The compiling step, of course, checks for syntax errors and generate an ASCII file containing the assembly code. You can see the hello.s file. Well, this optional option that I've used with GCC, this is used to specify the C language standard, whichever you want GCC to follow while doing the compilation. There are different standards like C11, which came in 2011. Other than that, we have C99, C90, famously known as the ANSI, and everything before C90 is Carnegie and Ritchie C, K&R. These standards add new features, improve old features, enhance security, and may standardize newly launched APIs. You can see the man page from chapter 7 about standards, and you can see different Unix and C standards over here. The BSD. Okay, over here we have C89, then you can see C99, C11, and different POSIX standards as well. And the newer one are the SUS, Single Unix Specification, Release 4. Okay. Whenever you have time, please do go through this standards page. Right now, we have successfully done the compilation and the output file is hello.s, and let me do cat hello.s. Okay, so you can view the assembly over here as well. Finally, once we are done with the compilation, the next stage is the assembling phase, and the assembler actually converts the assembly language to code to the machine dependent opcode. So let me do that as well. gcc-c option actually instructs GCC to do the assembling only. Let me add the option -g or -g gdb, which instructs to add the debugging symbols in the output file. And the input file is hello.s containing the assembly code. Let me do ls. You can see this file hello.o. The output of assembling phase is this .o file, and we call this file a relocatable object file, because the code section and data section of this object file will be merged with the code section and data section of other object files in the linking phase, which we will talk about later. This object file with many other things contains a symbol table that contains the name, type, and relative addresses of the global and static variables in the source file, if any. Name and relative addresses of functions defined in this file, hello.c file, and name only of library functions used in the source file, and whose addresses will be updated during the linking phase. That means this file will contain the name only, the symbol table of this file, hello.o, will contain the name only of printf function and not the address of the printf function. And that will come once we will do the linking. Okay. The fourth and the last phase is the linking phase. In very simple words, you can say that a linker actually links or merges multiple .o files or relocatable object files and creates a single executable. In our case, although we have a single .o file, but it has to be linked with another .o file that contains the code for the printf function that we have used in our hello.c file. Okay, you can see that. The code for this printf function resides in the standard C library. Let me do man7 libc. Well, libc is the standard C library. You can read this page out. glibc is the GNU libc. Please do read this page whenever you have time. And on my machine, the standard C library as well as other libraries are located in, let me move on to another terminal and let me go to that directory, usr lib x86 64 linux gnu. Okay, so here we have a lot of libraries in this directory. Let me do ls and let me pipe it to grep libc.so. Well, dear students, these libraries are pre-compiled set of functions actually, ready to be used by our programs. And these libraries come in two flavors. One is the static library and the other is known as the dynamic library. .so shared object is the dynamic version and .a archive is the static version. And you can see we have libc.a as well as we have libc.so in this directory. Okay, so let me show you that as well. Let me check out whether printf.o is there in libc.a. Let me use the librarian for this, libc.a, and let me grep printf.o. Okay, well, fine. So this libc.a standard C library contains over 1500 object files containing code of functions dealing with input, output, memory allocation, signal handling, date and time, and integer math. And you can see printf.o file which is there in this libc.a. Now we need to link this printf.o file from this library libc.a with our hello.o file, and this is what linking is. Okay, so we can do the static linking as well as the dynamic linking. So let me do the dynamic linking first. GCC hello.c -o with the name of dynamic exe, and let me do -lc. Well, this -lc option to GCC tells it to link it with libc.so. Basically, GCC will try to search for libc.so first. If it is there, it will be linked. If it is not there, it will search for libc.a. It will be linked. And if both are there, the default is that it will link with the libc.so. So by default, it will do dynamic linking. So if you want to force GCC to do static linking, you can use the -- static option. Let me name it static exe, and let me give the option -static, and let me do ls-l. Okay, lh. Let me see the sizes of both these. Well, you can see both these executables have been created. The size of dynamic exe is 8.3K, while that of the static exe is 792K. Okay, well, in case of static linking, the linker resolves all the external references and final executable contain the complete code. The final executable, having a big size, contains the complete code, and it can run even on machines not having this library, the standard C library. However, in case of dynamic exe having a smaller size, the final executable does not actually contain the code of external functions. That is, it do not contain the code for printf. That is why it is small in size. But to execute the library, but to execute this program, the library must exist on the system. Dear students, another advantage is the library code is shared among different processes running at the same time on the system. Okay, so well, linking is done. Now, what we need to do is we need to see all the intermediate files. We created this file. This is the pre-processed file, and we have used cat or less to view the contents. This file contains the assembly code. Let's see the contents of this file and this file now. Let me do cat hello.o. Cat cannot view the contents. Let me cat static exe, and well, the cat program cannot see the contents. Okay. Right, dear students, let's move on to the concept of the object files. This slide briefly describes the 4 types of object files. In today's session, we are more concerned about the relocatable object files and the executable object files. In some future sessions, we will talk about the shared object files and the core dump files, inshallah. Well, the object file formats may vary from system to system, and these are some of the famous formats. Well, A.out is the initial format used in the initial versions of Unix. That is why the executables are still referred to as A.out on all Unix-based machines. And then in System 5 Release 3, we have Common Object File Format, and in System 5 Release 4 and in today's Linuxes, we have the ELF executable and linkable format, and in Microsoft Windows, we have portable executable. Let's talk about the ELF format in detail. Well, dear students, executable and linking format is a binary format which is used in System 5 Release 4. It is a format that is used for storing programs or fragments of programs on disk, and later these are linked with each other. The executable file in this format consists of the ELF header, program header, and section header, and a lot of sections are there. All the files that are represented in this form are the .o files, A.out files, SO files, and the core dump files. Well, this diagram shows the different sections of a file that is saved in ELF format on your hard disk. Let us move on to the Linux terminal and see the contents of our hello.o object file using some command. Okay, let me clear screen. We have hello.o. Let me use a command read elf. This command is used to display information about ELF files. Please do go through the main page of this file. -a option is used with this to view all the contents of this file. You can see symbol table, headers, lot of information. Let me see these information one by one. Let me use -h option. Well, -h option displays you the header information, ELF header. The ELF header starts with a 16-byte magic number shown over here. This specifies how the linker or the interpreter is going to interpret this file, maybe the loader as well. And then you can see the class is ELF64, data is saved in tools complement little endian, and so on. The information in ELF header of the .o files are actually used by the linker to merge them together, and the information in the ELF header of the executable files are used by the loader actually. Well, You can see there are different sections, and how many sections we have? Number of sections, we have about 21 sections. Okay, so let us see a section using the hyphen capital S option. Hyphen capital S option is used to display the names of different sections in the object file. Let me move up a little bit. Well, it says there are 21 sections. Dot text section that contains the machine code. This section contains the machine code, and this section usually has read and execute permissions only. And this is the section that is most affected by optimization as well later on. Well, this dot data. This contains initialized global and static variables. .bss contains uninitialized global variables. It is named after IBM 704 assembly instruction, block storage start or block started by symbol. Since this section occupies no actual space in the object file, so some people call it better save space. Well, we have comments and debug. These sections are there just because we have compiled our program with the -g GDB option. Otherwise it will not be there. These sections will not be there related to debugging. Well, this sim tab is the symbol table. This section contains a symbol table, that is the name, type and relative addresses of the global variables, as I have said before, name and relative addresses of functions that are defined in this file, and name only of external functions like printf. For further details, you can dig out man pages of ELF as well as read ELF. Well, dear students, other than read ELF, we can also use another command, that is objdump. This can be used also to display information from the object files. Do go through the man page, see different options and what all you can do with it. Let me say objdump -h hello.o. So this again shows a section header, but in a bit different way. If you want to see the assembly, you can use the -D option with objdump. It shows you the assembly of all the sections, iframes, debug section, debug info, all the sections. The entire .o file is disassembled and displayed in front of you, and this is the assembly of main. Let me show you the assembly of main only by writing a small d over here. This is the disassembly of the main function. Well, by default it shows AT&T. If you want it to show in the Intel assembly format, you can use the -m option. Okay, now it shows the Intel assembly format. You can see the 4 main columns. These are the logical addresses. Then we have the machine code of each instruction. So this is the assembly format of that instruction, and these are the commands. Well, you can see these two instructions. Let me spend some time on this. Push and move. These two instructions actually creates a new stack frame on the stack. The purpose of this stack frame is to act like a boundary wall and isolate all the data created by the previous procedures. So actually these two lines create a stack frame for the main function. And finally, these two instructions, pop and return, these basically free or roll back that stack frame. And this is the actual call to the main. Okay. So we have used readelf and objdump command to view the contents of the .o file. We can use the same two commands to view the contents of the executable file as well, the static exe and dynamic exe. You can view the assembly using the objdump. Let us see how we can view the assembly of an executable by loading it in a debugger. Well, you all know that a debugger is a program running another program. And let me use GNU debugger, that is GDB, to see the assembly of our executable. If you don't know much about GDB, please go through my video session of GDB in C refresher. -Q is used for quiet mode. And let me load this dynamic XZ. So it has successfully read symbols. No debugging symbols found. Let me reading symbols. No debugging symbols found. Let me quit it. And let me do gcc -ggdb hello.c. Okay, and let me do now gdb -q a.out. Okay, so it has read the debugging symbols. Fine. Let me disassemble the main function, and you can see the disassembly of the main function. Let me set the assembly flavor as well. Set disassembly flavor to Intel, and let me disassemble main again. Okay, now you can see the disassembly. It appears to be the same, but right now over here you have the addresses. Let me take this opportunity to show you the registers as well. Let's see the registers. Let me put a break in main and let me run it, and let me use info registers. Okay, so you can see 16 64-bit registers. These are the general purpose registers. RAX, RBX, RCX, RDX, RSI, RDI, RBP, RSP, and so on to R15. Then we have the famous instruction pointer. We have the E flag register, and then we have 6 segment registers: code segment, stack segment, data segment, and so on. For floating point operations as well, there are other registers as well. Let's see those registers. And let me say info all hyphen registers. Okay, you can see we have ST1, ST0, ST1, ST2. These are the 80-bit registers, about 8 registers. And then we have YMM0, YMM1, YMM2, and so on to YMM15. We have 16 256-bit registers. Well, let me continue. It has successfully executed, and let me quit. So we are back. Okay, dear students, so far so good. We have seen the C compilation process in detail. We have seen the contents of all the intermediate files and the final executable. The one thing that is left is copying the program file from hard disk to main memory and make it a process to execute. /dynamic.exe. Welcome to System Programming with Arif Bhatt. Let us move on to the slides and see this loading phase in a bit detail. This slide shows the ELF format of the executable file. This is the file that is stored on disk. We have seen the contents of this file using the objdump and read ELF command. And over here we have the logical address space of a process. Well, dear students, remember the code section or the code segment always starts from address 804800 for all 32-bit Linux systems. After the data section, over here, the heap grows up, and the memory map region grows up from address 400000. The user space is up to the address BFFFFF. Up till from 0 to BFFF, we have the user space, and the stack always grows down from this address. Everything above this address that is from C000 to all Fs is the kernel space, and the kernel space, which is not visible to the user code, is divided into 2 parts. The kernel code itself and its data structures, which are same for every process, and process specific data structures, which are different for every process. For example, uh, uh, this page may contain the task struct for this process, the page table, the memory management structs, the kernel stack for this process. Well, there are different addresses and different variables as well. Probably in some next session we will talk about them in detail. Okay, so now this process is loaded in memory, and it waits for its turn in the ready queue, and when its turn comes for the first time, the execution starts from the address of underscore start symbol. The startup code, dear students, is defined in an object file of the kernel code, that is crt1.o. This crt1.o is located in the standard C library libc.a, and the pseudocode is shown over here. Well, you can see the program entry address is 8048 first of all, different startup routines from .text and .init sections are called, and before calling main function, different exit handlers are registered, and after the main exits, the exit handlers are executed. In some later session, we will see details about these exit handlers, inshallah. Okay, dear students, I am sure by now you have a fair idea of C compilation process, especially how the different library functions that you use in your programs are linked with the final executable. Let us change gear and talk a bit about system calls as well. Man to intro. Every section of man page has an intro page that describes that particular section. Well, this page gives an introduction to the system calls, which is an entry point into the operating system kernel. Do read this page whenever you have time. It will be very informative. Let us see the list of the system calls now. List of the system calls that are available in different versions of Linux kernel. Let me do man syscalls. Okay, so system calls and library wrapper functions. Let me move down. System calls are generally not invoked directly, but rather via wrapper functions in glibc or some other library. And we have the system call list coming down, and it tells you the different versions of the kernel and which system call comes in which version of the kernel. Okay, so over here you can see different system calls. The seek system call, access system call, bind, brk, and so on. There are a lot of system calls. Let me search for a system call that we call write. There are different versions of write, pwrite. We are interested in the simple write. Well, yes, over here we have write. So you can see this is the system call I'm interested in. Write system call. This came in Linux kernel version 1.0. Well, if you want to use any of these system call wrappers, you can view the respective man pages. Let's view the man page of the write system call. Man to write. 2 is because I want to see this in the man page section 2. Section 1 also contains information about the write command. Well, the write system call is passed 3 arguments, as you can see over here. First is the file descriptor. The file descriptor of an already opened file to which you want to write. Next is a pointer to the buffer containing the data or characters to be written. And the third is the number of bytes to be written. Do read the man page. See the return value. On success, the number of bytes written is returned, and in case of error, a -1 is returned, and error number, which is a global variable, is set appropriately. You can check this error number against these constants to find out what error has happened. E again, in case of non-blocking call, E bad F is FD is not valid file descriptor and is not open for writing. E fault maybe the buffer is not inside your accessible address space. E interrupt is because the call was interrupted by a signal before the data was written, and there are other errors as well. Do go through the main page of the system calls whenever you are using them, and do see all possible errors that can be there in case if this call fails. Well, let us see a basic program now. Let me do cd and let me move on to system calls, and let me move inside this to using wrapper. Okay, so I have program wrapper.c. Let me cat it. Okay. You can see I am adding the file unistd.h. Whenever you're using a system call, never forget to include this file. You can see the write system call over here. I'm writing a string to the file descriptor 1, which you all know is the standard output. The string is pointed to by this address and the size of the string over here. And the write returns the number of bytes written on stdout. And finally, the main function returns the number of bytes written to its parent, that is a shell program. Let me compile this program. GCC wrapper.c, and let me execute it. A.out. Welcome to system programming with Arif Bhatt. Let me do echo $? And you can see 49. Well, you know, we can see the value returned by a child program to its parent, that is a shell, in the environment variable $? Which right now contains 49, as you can see. And actually, these are the number of characters in this string. Okay, dear students, we will be using system calls by calling their appropriate wrapper functions, like we have just done. In the entire course, we will be using these wrappers. But to understand how system calls are actually called, let's dig out a bit deeper and see how we can make a system call without using its library wrapper. We can do this using the syscall system call. Let me clear screen and let me do man syscall. Okay, you can see the syscall system call can be used to invoke a system call that has no corresponding wrapper function in the C library. This syscall can be passed variable number of arguments. The first is the number of the system call, and followed by the arguments that are passed to the system call. Let us move down and see. We have we have the architecture calling convention. This table describes actually the calling convention for different architectures. R is x86-64. Okay, over here. Yes. So you can see that for x86-64, the system call number will be placed in RAX register. System call number will be placed in RAX register, and the return value will also be placed in the RAX register once the system call is executed successfully. Okay, let me move further down on this page. Okay, ours is again x86-64, and this table shows the registers that are used to pass the system call arguments. Yes, x86-64. You can see in this case the argument 1 will be placed in RDI, argument 2 in RSI, argument 3 in RDX, and argument 4, 5, 6 will be placed in R10, R8 and R9. So we can pass 6 arguments to to any system call to the max using these registers. In case you want to pass more arguments to a system call, you can use pointers. Now let us try calling the right system call without wrapper and use this syscall instead for this. And for this I need to find out the system call number of right system call first. And it is there in USR include x86, 64 Linux GNU, ASM and UniSTD underscore 64.h. So this is the file which contains the system call numbers, and you can see read has a system call number of 0, write has a system call number of 1, open 2, close 3 and so on. You can see all the different system call numbers over here, and we have 331 system calls. Fine. I have written a program for this which is syscall.c. Let me do cat syscall.c. Okay, so you can see I am calling syscall. This first argument is the system call number of write, that is 1, and these are the 3 arguments to the write system call. You can use the system call number, or you can use this constant as well, which is also defined in bits syscall.h. Let me do gcc syscall.c, and let me do ./a.out, and let me do echo $? Welcome to System Programming with Arif Bhatt. Okay, dear students, we have invoked a system call using a C library wrapper, which is a normal way of calling it. We have also invoked a system call using the syscall system call, which is used to invoke a system call that has no corresponding wrappers in the C library. And one thing that is left is invoking a system call from within an assembly code to actually understand how the arguments are placed in the registers. Let's do this as well. Let me do cd from assembly, and we have the code syscall.nesum. Let me do cat syscall.nesum. Okay, so this is the code. You can see a symbol, a global symbol main, then you have the data section, and then we have the text section containing the code. Well, in the data section we have a simple string, and then we have this instruction. Let me highlight this instruction and tell you what it's doing. EQU is actually used to define a symbol. This dollar evaluates to the current line, and this message evaluates to this line. So the difference of these two means the size of the string. Fine. In the .text section, you can see over here, I am doing what? I am placing 1 in RAX. That is, I am placing the right system call number in the RAX register. Then in this instruction, I am placing the first argument to the right system call in RDI, that is the file descriptor 1. The second argument, that is the message string, is placed in the RSI register. And finally, the third argument, that is the number of bytes to be written, len message, are placed in the RDX register. So AX contains the right system call number, RDI, RSI and RDX contains the first, second and third argument to the right system call. Then this instruction syscall will actually cause the trap machine instruction to switch to the kernel mode. The trap handler will index a system call table with the system call number in RAX and will execute the right system call code. So this will be executed. To be on the safe side, I have placed the return value of the right system call from RAX to R15 so that I can return it to the main. Well, these 3 lines now are actually calling exit with the return value of the right system call. The system call of exit is 60. You can check it out on the file. and there is only one argument that is placed in RDI, and that is the return value of the write system call, and which we saved in this register. So let me assemble this assembly code, and let me use the NetWide assembler for this. Let me clear screen, do again this cat syscall. Let me do nesum -f elf64, the file format syscall.nesum. This will generate syscall.o. That is a relocatable object file which needs to be linked with the standard C library now, because we are calling the printf and the exit calls. Let me use ld syscall.o -o myXZ. Let me do myXZ1. Okay, it is just giving me a warning because the Linux linker LD, it expects the entry symbol to be _start while we have used main instead. But it has, of course, generated the executable file. Let me do GCC instead, syscall.o -o, and let me name it myXZ2. Well, the GCC expects the main symbol, so that's why it has not given any warning. We have the two executables in front. Let me execute /myXZ1. Welcome to system programming with RFBut, echo $, and the return value to the parent shell is 49. Okay, dear students, so that is all for this session. If you have liked it, please subscribe my YouTube channel and share it with your friends. Wish you all the best. Happy learning, and Allah Hafiz.